Hello students, welcome to the series of organic chemistry lectures. Dear students, we have been learning organic chemistry chapters under alcohols, phenols and ethers. Today we are going to learn phenols. So what are the phenols? Phenols are the hydroxy compounds attached to benzene ring. So this is the benzene ring attached to OH bond. So hydroxy group is attached to benzene ring and the oxygen is sp3 hybridized oxygen, and whereas the carbon is sp2 hybridized. So the bond angle of this is about 109 degrees and the bond length of this sp2 carbon and oxygen is 136 picometers. As we know, CC single bond length is 154 picometers and CC double bond is 134. Yes, so it is between these two bonds length, because sp2 hybridized carbon and this lone pair electrons are tend to undergo resonance and it is going to be formed similar to double bond O. That is why the bond length of this is in between tetrahedral bond length, that is CC single bond and C double bond C length. This is phenol or monohydric. Benzene, if it is having one hydroxy group, then it is known as monohydric, and it can have other substituents like orthocresol, metacresol, and this is paracresol. When it comes to dihydric phenols or dihydric benzenes, it is having two hydroxy groups. If it is ortho to each other, then this compound is dihydric phenol. Two hydroxy groups can be ortho to each other, meta to each other, or para to each other. Based on their position, the names will differ. It can be trihydric also. The phenols can be trihydric. If it is continuous, that is 1, 2, 3 triol, 1, 3, 5 triol, and this is 1, 3 and 4. So what are the names? When it comes to the common name of this phenol is phenol only. Common name and IUPAC name of phenol is same, phenol. Whereas this is orthocresol. Why ortho? This is ortho position and this is meta and this is para. So with respect to hydroxy group, the methyl group is ortho. So the common name is orthocresol. This is metacresol. This is paracresol. When it comes to IUPAC nomenclature, 2-methyl phenol, 3-methyl phenol, and this is 4-methyl phenol. Yes, when it comes to these dihydric phenols and these trihydric phenols, the names are very specific names. The name of this compound is catechol. The common name is catechol, and this is 1,3 position resorcinol, and this is quinol. And the IUPAC names are benzene 1,2 diol, benzene 1, 2, 3, 1,3 diol, and here benzene 1,4 diol. Like this you have to give the nomenclature. When it comes to these trihydroxy benzenes, 1, 2, 3 trihydroxy benzene, pyrogalol, this is fluoroglucinol, and it is 3-hydroxy phenol. Yes, so the IUPAC names of these compounds is different. How? It is benzene 1, 2, 3 triol. This is benzene 1, 3, 5 triol. This is benzene 1, 3, 4 triol. Dear students, these are the only possibilities where you can arrange these hydroxy groups. For example, this hydroxy group, if I keep here, then it also becomes 135. If I this hydroxy if I keep here, then also it becomes 1, 3, 4. So these are the arrangements of monohydric, dihydric and trihydric phenols. So let us see the preparation of phenols. Preparation of phenols. Halo-Arenes upon treatment with sodium hydroxide undergoes substitution. This substitution with hydroxy group is not that easy. However, at high temperature, that is 350 degrees centigrade, around 350 degrees centigrade, under 300 atmospheric pressure, to give sodium salt of phenol. This sodium salt of phenol upon treatment with HCl, it gives phenol. So this is one of the ways for the preparation of phenol. Another method, available method for the preparation of phenols is from benzene upon treatment with oleum. What is the chemical formula of oleum? H2S2O7. It undergoes sulphonation. This sulfonic acid upon treatment with NaOH, this easily replaceable, students. This hydroxy group replaces sulfonic acid to give sodium salt of phenol. This sodium salt of phenol upon treatment with HCl, it is going to give phenol. Yes? And the other methods for the preparation of phenols known is diazotization method. How to make diazonium salts, aniline upon treatment with aqueous HCl, sodium nitrite, NaNO2, maintaining the temperature at 0 degrees centigrade to 5 degrees centigrade. Less than 5 degrees centigrade, it is going to form diazonium salt, diazonium chloride. This diazonium chloride, since the reaction mixture is in water, form it. This is going to form phenol and nitrogen is out plus HCl. These are the usual methods for the preparation of phenols. However, commercial phenol is prepared from cumene. Yes, students, let us see the preparation of phenol from cumene with mechanism. Cumene Hydroperoxide process for the preparation of phenol. This is commercial method, students, where this cumene is nothing but, what is cumene? Isopropyl benzene. This isopropyl benzene is nothing but, this is having isopropyl benzene, where it is having labile hydrogen. This highly labile hydrogen, upon losing this hydrogen, this carbon is stabilized because of tertiary nature. If it forms free radical or carbocation, it is going to be stable, tertiary free radical. At the same time, it is benzylic also. That is why it easily undergoes aerial oxidation with oxygen to give cumene hydroperoxide. This intermediate structure is very, very important, students. It has been asked in so many entrance exams. So this is CS3. This cumene hydroperoxide, upon treatment with H plus and water, it is going to give phenol plus it is going to form acetone. This is cumene hydroperoxide. The intermediate structure is cumene hydroperoxide. So this cumene hydroperoxide undergoes some rearrangement reaction. In presence of water and H plus, it is going to give phenol. Let us see the mechanism of this reaction. So this cumene, in presence of oxygen, loses hydrogen free radical. How to write hydrogen free radical? So generation of free radical takes place under aerial oxidation. So that has to be written with half fish hook. Yes, the arrow should be written as half fish hook, right? So to give this cumene free radical, this cumene free radical is stable and minus hydrogen free radical. This cumene free radical is going to take up oxygen and this oxygen is going to undergo homolysis, hydroperoxide intermediate. This is going to form O and O, this is free radical is here. And this free radical, now it takes up hydrogen which is there in the reaction mixture to form cumene hydroperoxide intermediate. This is the structure we are going to get at this stage. Now when I add water, when I add H plus ions to this oxygen takes a proton to form an intermediate. This is hydroperoxide, and O, hydrogen is here. Now this is, so this oxonium ion is going to lose water molecule minus water, and what is the charge on this now? So this oxygen is going to attain positive charge. To satisfy that positive charge, this phenyl ring along with this bond is going to migrate or rearrange onto this oxygen. Then what is the charge on this carbon? It is going to be positively charged. Let me write here. So this phenyl ring, and now it is attached to this oxygen, and previous it is here. This is positively charged now, right? So this positively charged molecule is going to take up water which is there in the reaction mixture to form this intermediate. So I am straightening this oxygen. Yes, so this side, let me write this double bond, and water is attached here. This water molecule now undergoes tautomerism. What is going to happen? It is going to take up this proton, and here it is going to form this tautomer. This mechanism is very, very important, students, with respect to your board exams, or even with respect to your entrance exams also, because it has been asked so many times. The intermediate structures. So this is the intermediate. Now what is going to happen is it loses this proton. What is the charge here? Because it is having positive charge, it takes up this bond to give, this is the phenol, oxygen and OH, and here the remaining is going out as double bond O. So the what is the outcome? The overall outcome is phenol and acetone. So acetone also is a very, very important solvent, industrial solvent, or it is commonly used for washings. At the same time, it is a starting material for the different types of organic compounds. Students, properties of phenols. So the boiling points of phenols increases with respect to increase of hydroxy bonds or hydroxy groups. If I take this phenol and resorcinol, so this is phenol and resorcinol, the melting point of phenol is about 41 degrees centigrade, whereas resorcinol melting point is 110 degrees centigrade, and the boiling point of this is 182 degrees centigrade, whereas resorcinol 277. Yes, students, so the boiling point increases as hydroxy groups increases. The boiling points or melting points are higher than the other compounds like hydrocarbons. What are the hydrocarbons we have learned? We have learned alkanes, alkynes and alkenes. At the same time, it is higher than halo-arenes and alkyl arenes. Not only this, the boiling points and melting points are higher than aryl ethers, aryl methyl ethers. Then why the boiling point or melting points are higher with respect to other compounds? It is because presence of intermolecular hydrogen bonding. Intermolecular hydrogen bonding takes place between two phenols. For example, this is one phenol and it is going to form hydrogen bonding with another phenol molecule, and this is another phenol molecule. So Because presence of this intermolecular hydrogen bonding, the oxygen of one phenol bonds with hydrogen of another phenol molecule. So this is intermolecular hydrogen bonding. And this intermolecular hydrogen bonding is concentrate dependent. That means if the solution taken of phenols is concentrated, the intermolecular bonding will be very strong. If this phenol solution is diluted with some organic or water molecule, then this intermolecular hydrogen bond is going to be very far, means two molecules are very far to each other. This hydrogen bonding going to be weak. So this hydrogen bonding will be detected by IR spectroscopy. Dear students, IR spectroscopy gives strong hydrogen bond stretch at about 3300. So if it is intermolecular, it is going to be shift towards 3000 and it is going to be vanished in dilute solutions. Anyhow, it is independent of these phenols, but you may get this way also. So how to differentiate intermolecular hydrogen bonding and intramolecular hydrogen bonding of phenols? Yes, so it can be done by IR spectroscopy. And this intermolecular hydrogen bonding is concentrate dependent. Phenol is water soluble. Why it is water soluble though it is aromatic compound? Because of this hydrogen bonding. So when water molecule comes to near to it, it is going to form hydrogen bonding with water. So phenol is water soluble. However, cresol and other molecules which are substituted with alkyl or aryl groups, they are going to be insoluble with water. Acidity of phenols. Phenols are acidic. When you take phenol and treat it with metal like sodium, it is going to form sodium phenoxide plus hydrogen is going to be evolved. And not only this phenol can form salt with sodium hydroxide to give sodium phenoxide. And here the important thing is, yes students, it forms salt with strong acid like NaOH or KOH, whereas it will not form salt with sodium carbonate. No salt formation, and it is also not going to form weak base like sodium bicarbonate. So there is no salt formation with these two bases. Then why it is going to form this salt? Because upon salt formation, what is going to happen? It is going to act as Bronsted acid. What is Bronsted acid? Bronsted acid is proton donor. It loses H plus ions to give this phenoxide plus H plus. So this phenoxide itself is resonantly stabilized because presence of this lone pair electrons, it is going to have resonance structures. So what are the resonance structures? If you write phenol resonance structures, double bond and it is positively charged, this is going to have resonance structures like this. When this anion comes here, it forms carbanion at para position, and this further arrangement it is going to form, and this is OH, here OH and double bond, and this is can be stabilized like this. So phenol itself is having these many number of resonance structures. At the same time, this phenoxide ion, how many structures are there? If I say this is 1, 2 and 3, 3 structures are possible, resonance structures are possible for phenol. However, phenoxide ion is going to have more number of resonance structures. Let us see. Phenoxide ion upon resonance stabilization, so it is going to form, it is carbanion. Yes, so this carbanion can have this para position carbanion, and this is further going to have this structure. It is nothing but it is going to have this structure. So how many structures are possible for this? 1, 2, 3 and 4. So phenol, upon losing H plus ions, it is going to have 4 resonance structures. That is why it is common to say that phenol exists in the form of this oxide ion. So it easily loses H plus ions. Because losing of this H plus ions, it is going to have stable oxide ion. This oxide ion is going to have resonance structures more than the phenol. So acidity of organic molecules can be denoted by pKa values. As the pKa value is low, pKa strong acid, high pKa value weak acid. So when you take overall organic molecules, acidic molecules, the first and foremost compounds acidic are carboxylic acids. Carboxylic acids pKa is going to be around 0 to 6. So these are strong acids. When it comes to phenols, is going to be around 10. And then it is going to be alcohols. The pKa of alcohols is going to be 15, then followed by alkynes. The pKa is going to be around 20. Yes, this is the overall acidity order of these compounds. Then, what is the substituent effect? Is phenol if substituted with electron withdrawing group or electron donating group? What is the effect? Yes, students, it is going to have substituent effect. That means electron withdrawing group increases acidity or acidic strength. For example, nitro group. So, if the phenol is substituted with the nitro group, it is going to have low pKa value, or at the same time it is going to have highly acidic nature, and that too ortho and para substituted nitro compounds are going to be highly acidic, whereas meta is not going to have that much effect. If you take electron donating group or electron releasing groups, decreases acidic strength. For example, methyl group, methyl or ethyl alkyl groups, or methoxy group, like these compounds are going to have electron donating nature, so these groups are going to have less acidic strength. Let us take some compounds and see. And a highly acidic compound, which is, though it is not acid, it is named as picric acid. Trinitrophenol is known as picric acid, and its pKa value is about 0.38 pKa. So picric acid is very strong because the negative charge during the resonance structures of phenol is going to be shared by these nitro groups at ortho and para position. And this follows, for example, mono substituted. If I take this para nitrophenol, it is going to be 7.1, and then follows ortho nitrophenol 7.2, then it is meta nitrophenol is acidity or pKa is about 8.3. Phenol, what is the pKa of phenol? It is 10. If it is substituted with electron donating groups, for example, let me add this methyl group, and this methyl group, if it is at meta position, it is going to be better acid or strong acid when compared to ortho or para. So ortho and para is going to be around same, whereas this metacresol is more acidic than ortho and paracresol. It is very important key point, students. So metacresol is more acidic than these ortho and para. Esterification. So how to do esters? Let me take this phenol, and this OH bond is going to be replaced with acyl group. For example, if I take acetic acid, in presence of H plus ions, it is going to form acetate, phenyl acetate. And is this the only method to make esters of these phenols? In place of acids, you can take, this is constant, students, acetic anhydride or any anhydride. Anhydride in presence of H plus, it is going to form acetate. And this acetate group esters are known as acetylation of phenols. CH3CO2H, and it can be written as acetic acid. Or I can use acetyl chloride. For example, acid chlorides can be used. And this acid chlorides in presence of pyridine has to be done because it is going to release HCl is going to be out, and this HCl breaks these esters to back to phenols. Ester hydrolysis is going to be take place. So the HCl what is going out has to be quenched or neutralized by phenol. That is why pyridine has to be used here. Plus HCl. This HCl makes salt with pyridine. Since it is base and it is acid, so it is going to form salt with HCl. Acetyl salicylic acid. Preparation of aspirin. Aspirin can be prepared taking salicylic acid. Orthohydroxybenzoic acid. The common name is salicylic acid. Salicylic acid upon treatment with acetic anhydride. This is acetic anhydride. So acetic anhydride you may get like this. It is going to form aspirin. What is aspirin? Yes, you might have learned Dispirin tablet. So this Dispirin tablet is going to have acetyl salicylic acid is nothing but aspirin. Acetyl salicylic acid is aspirin. Aspirin is a pain reliever. This aspirin is analgesic and antipyretic, and this aspirin is used for the treatment of heart attack. And what is left over? It is going to be out as acetic acid, CH3CO2H. This hydroxy group is of phenol. This oxane is not coming from this. Yes? So it can be cross-checked by substituting this isotopically labeled oxygen phenol, and it is found that it is there in phenolic OH, and the bond during acetylation is going to break this OH bond, and it is not going to break this carbon and oxygen bond. This carbon and oxygen bond is not at all going to break, only except in one reaction where use of zinc it oxidizes. Otherwise it is very strong. Because of this resonance it attains like double bond character. Let us see the chemical reactions of phenols. Yes students, phenols undergoes electrophilic, aromatic, substitution reaction. For example, nitration, halogenation, sulphonation. So these are the common reactions. And what is the orientation of phenols? Phenols are activating groups, and these are ortho and para directing group. Just now I have shown during the resonance structures you will get negative charge at this place and at this place. The incoming electrophile takes up this anion or nucleophilic nature to undergo electrophilic aromatic substitution reactions. Electrophilic aromatic substitution reactions involves 3 steps. Generation of electrophile. For example, if I take bromine and I use ferric bromide as Lewis catalyst, it forms bromine electrophile. This is electrophile. I can write it as E plus ferric bromine minus. Yes? And if I take nitric acid, it is going to form HNO3, and it is going to take up this proton and it is going to form HSO4 minus plus, and this is OH and NO and hydrogen, it loses minus water, it is going to form nitronium ion. Yes, so this is also one electrophile. The second step under electrophilic aromatic substitution is formation of aryl carbocation or sigma complex. What is going to happen in this case? It is going to form, for example, this is phenol and it is electrophile. It takes up this and it is going to form carbocation. Hydrogen is here. These are all the resonance structures, students. Now it is E and here hydrogen is here. It is takes up. It is going to give this resonance structure of this E. It is nothing but it is sigma complex where positive charge is there in the ring. At this stage, it is going to the third stage. Third step involved in this reaction is removal of hydrogen. So take this intermediate. It is having OH here and electrophile is attached and here hydrogen and this is positive charge. In presence of, for example, ferric tetrabromide bromine anion and this hydrogen takes up and minus H plus. This H plus is going to be taken by bromine and now we are with electrophilic substituted compound. It can be nitro group or bromo group and this is electron and this is HBr plus ferric bromide and this is going to act as further as acid catalyst. So this is how electrophilic aromatic substitution reaction takes place where you will have three stages. So the first stage of electrophilic aromatic substitution is generation of electrophile. Second one is formation of carbocation complex, a sigma complex. The third stage is removal of hydrogen. Let us take based on this. Let us do nitration and bromination and sulfonation. If I take phenol and do the nitration with dilute HNO3, since it is highly activating group, there is no need to add sulfuric acid also. Fuming nitric acid or even dilute nitric acid also is enough to undergo nitration to give OH, ortho and mixture of this para. Ortho para directing group. So we will get this mixture of these two compounds. Then how to separate these two compounds? It is very simple, students. Since it is ortho compound, it is going to have intramolecular hydrogen bonding. Ortho compound is going to have intramolecular hydrogen bonding. So this hydrogen bonding works as like jig or hook like this and it can be separated by steam distillation. Because presence of this intramolecular hydrogen bonding during steam distillation, it easily takes up water. Ortho compound low temperature distills out. So the first outcoming compound is ortho compound during steam distillation because of this intramolecular hydrogen bonding. Then the leftover compound distills out. This comes out later because there is no intramolecular hydrogen bonding, though it will have intermolecular hydrogen bonding. Yes, friends? So this ortho para mixture can be separated by steam distillation. Instead of this dilute nitric acid, if I use concentrated nitric acid HNO3, I am going to get trinitrophenol. What is trinitrophenol? Picric acid. So once the first step of this excess nitric acid when I use, phenol is going to form picric acid. However, the yields are very low yields because once this nitration takes place at ortho and the remaining nitro groups is going to take place very slow. Yes, dinitration requires sometimes heating also. To overcome these low yields, what we can do is do the sulfonation first, fuming sulfuric acid, then do sulfonation. It is going to give this OH and SO3H and this is SO3H. So disulfonic phenol we are going to get. Then when you do nitration now, so the first step what is going to happen, it easily takes up nitro group here and these two sulfuric acids are easily replaceable with nitro group so that the yields of this picric acid is very high. So this is metacresol. If I ask you to do mononitration, where it goes? mono nitro compound, nitration. Yes, let me use dilute HNO3 because it is ortho position and this is para position, this is ortho position. Which side it is going to undergo? It is very simple, students. So in between this, OH is here and methyl group is here. So it is one bulky group and this is also one bulky group. So coming in between this is not going to take place. So this nitro group is not going to form. And what is left over? It may undergo nitration, para to phenol plus and ortho to phenol. And one more key factor is, as I said, this methyl group. What is the orientation of methyl group? Methyl is electron donating group. It also orients the electrophile to orthopara. So that is why it is going to form these two mixture of these two compounds. Then again, how to separate this? So this ortho compound is going to be steam distilled out first, then it is para. Then if I ask dinitration of this compound, where it takes place? It is going to undergo dinitration at these two positions. Dinitration, it is going to take place at this position. Dinitro compound you are going to get because this position is blocked. The incoming nitro group is very tough to enter into this carbon. If I substitute this phenyl acetate and do the nitration, mononitration, yes, where it is going to undergo? So this phenyl acetate also orthopara directing group. So it is going to form major product para position. Yes, students. So this is how para nitro, this phenyl acetate you are going to get. Let us see bromination reactions. Yes, bromination or halogenation. Let us take bromine as an example. So bromination depends on solvent. If I use bromine in carbon disulfide, it is a solvent. Carbon disulfide is a solvent which is having about 46 degrees centigrade boiling point. Or if I use chloroform CHCl3, the boiling point is about 65 degrees centigrade. So if I use these solvents, it is undergoes monobromination or monohalogenation, OH, and it is going to form ortho plus para. However, it is said that para bromo compound is going to be formed major because the ortho group is, this bromine is very big molecule. Though it forms, the amount is going to be less. So it is going to be major, para is going to be major, and it is solvent dependent. Yes, students, if I do the bromination with bromine in water, then it is undergoes tribromophenol. Usually bromination of aromatic compounds, for example, this is R group is here, we required bromine plus Lewis acid like ferric chloride or ferric bromide. Lewis acid is required. However, phenols is strong activating group. It easily accepts electrophiles or it welcomes electrophile without using this ferric bromide, and phenol itself makes this bromine into electrophile. Yes, so that is why you may not find ferric bromide on arrow. So this is how it is solvent dependent. If I use carbon disulfide or chloroform, it is going to give this monobromo compound. If I use bromine in water, it is going to give tribromophenol. So sulfonation is what we can do, fuming sulfuric acid or oleum. Oleum, if I use, it is going to undergo sulfonation, this mono, di and orthopara. The mixtures you may get, or if you use excess, it is going to take this sulfonic acids. Sulfonation is going to take place. This sulfonic acid compound, upon nitration, we prepared picric acid. Yes, students, Kolbe's reaction of phenols. So where in this reaction, let us take phenol and react it with sodium hydroxide. It is going to give sodium phenoxide. This sodium phenoxide is going to undergo electrophilic substitution. So it is neutral electrophile to undergo neutrophilic substitution in presence of carbon dioxide. This is carbon dioxide is nothing but dry ice. Dry ice we will get as solid and add this dry ice into the reaction mixture. It is going to form OH and this is OH. This is salicylic acid. And what is the mechanism in this reaction? Dear students, so this O sodium phenoxide plus carbon dioxide, it is going to attack onto this carbon. It forms this to give phenoxide ion. Let me write here itself. This is carbon and O minus. This tautomerises to give O minus and O sodium salt. And when I add HCl, it is going to form phenol and this is carboxylic acid. This is salicylic acid. During aspirin preparation, we wrote like this. So both are same compound, students. So this is OH and here I wrote OH. So both are same compounds, one and the same. Yes, this is salicylic acid. Orthohydroxybenzoic acid or salicylic acid by Kolbe's reaction of phenols. Riemer-Tiemann reaction of phenols. What is going to happen? Let us take phenol, and this is common question appears in all your entrance exams. Phenol upon treatment with chloroform plus NaOH, or you may get KOH at about 60 degrees centigrades. It is going to form orthohydroxybenzaldehyde. This is salicylaldehyde plus para-hydroxybenzaldehyde. So salicylaldehyde is going to be formed. This reaction is known as Riemer-Tiemann reaction. Let us see the mechanism of this reaction. So the first stage is generation of dichlorocarbene will be formed. This is chloroform. Yes, when we are using strong base NaOH, the electron density of carbon is withdrawn by these chlorine groups. 3 chlorines will withdraw the electron density and this hydrogen easily goes out, will be taken out by this hydroxy group to form carbanion. This carbanion minus chloride to form dichlorocarbene. This is active species dichlorocarbene. This dichlorocarbene now undergoes substitution with phenol. So what is going to happen? Phenol plus chlorine. Since we are using sodium, it is going to have sodium phenoxide and this is going to be taken out by this to give takes up water to form, and this tautomerises further to give the intermediate where it takes up, and this hydrogen comes here OH and this CH dichloride. This intermediate, you will find this intermediate in your reaction textbook, students. This dichlorocarbon upon hydrolysis, what is going to happen? This in presence of base, since we are having base, this is going to be replaced by hydroxy group, where diol you are going to get. If you want, I am going to write the intermediate because in most of the textbooks it is not given. Hydrogen, OH and OH. This type of diol you may expect, and it is going to lose water molecule to form this aldehyde. What is the aldehyde we are going to get finally? It is salicylaldehyde. Salicylaldehyde is very important synthetic compound. Salicylaldehyde upon oxidation it is going to give salicylic acid. That salicylic acid is nothing but we are going to make aspirin also. Reaction of phenol with zinc. When I add zinc dust, it is fine dust we will get, student. Zinc is like powder, like iron powder. It will be like zinc dust we will get in laboratory. So zinc dust, it is going to form. So oxygen is going to be taken up by zinc. So it going to reduce. So zinc oxide is going to be formed. This is one of the reactions where this bond is going to be break or cleaved. Then how to prepare from benzene to here? We did by using oleum. We made sulfonic acid. This sulfonic acid upon NaOH reaction we prepared phenol. Yes, so phenol can be back to benzene by zinc. Sodium dichromate. Sodium dichromate Na2Cr2O7 is going to oxidize phenol to this phenone, benzoquinone. Yes, students. So this is how oxidation of phenol can be done using sodium dichromate. Dear students, I hope you enjoyed this topic. Please subscribe my channel Venus Academy if you are not yet subscribed, and don't forget to click on like button and bell button. We will meet again with a new topic, most probably ethers. Till then, bye. Have a nice day. Arigato gozaimasu.